Hello, professors. This is the presentation for the ENGI 990A for Group B1, consisting of Raymond Orie, Lena Otabil, and Jonathan Agoria. Our instructor or supervisor is Dr. Tariq Iqbal. The title of our project is Design and Analysis of a Hybrid Energy System for Cartwright, Newfoundland. The summary of contents are shown below. We have the objective, the introduction, the site details. And then we'll talk about the methodology as well as the system configuration. And then we'll talk about what went into the designing of the system. Now we'll move to the dynamic modeling, results and conclusion, and then we're going to acknowledge our references. The objectives for this project, there are a number of them. We have about 5. The first one is to model a hybrid system to generate enough power to meet the energy demands of a remote location. We chose Cartwright. And then we'll be selecting the best solution for hybrid sources. We would also determine the energy load requirement for Cartwright, Newfoundland, Canada. And then we'll model the system setup using Homer Pro. We also sought to simulate the designed model for performance evaluation with MATLAB. I would introduce the hybrid power system. It integrates multiple energy sources. A hybrid energy power system integrates multiple energy sources such as renewable sources like solar, wind, and hydro with conventional sources. The conventional sources could be the diesel generators and the natural gas. It generates electricity, and the aim is to optimize the energy production, enhance reliability, and to reduce the environmental impact by leveraging the strengths of each power source. Why did we design a hybrid power system? Because it is efficient and reliable, and then it combines multiple energy sources. It also integrates energy generation and storage. It gives a clean source of renewable energy, and it is a great resource to generate energy in remote locations like Cartwright. And finally, it has no damaging effect on the environment. So on our slide, we can see the map of Cartwright. This is an isolated community in southern Labrador, isolated from the province's primary electricity generating facilities. The community's main source of income is fishery. The diesel plant is the main source of generation of electricity. For that reason, they have 4 generators. We have 450 kilowatts, 2 of those, and 600 kilowatts and 1,050 kilowatts operating currently to supply electricity. The total diesel consumption by the plant amounts to about 1.2 million liters per year. This hybrid system can help to reduce the electricity cost. Now, Cartwright relies on ferry service. The next slide is showing the site details of our choice of hybrid system. The most suitable energy source for this hybrid power system is solar, wind, and diesel power. We chose higher elevations because they provide stronger wind flow in the case of wind turbines. A potential source of solar energy is another consideration we put when selecting the site details. We also put the consideration of existing diesel generators on site. The hybrid power system will use solar, wind, and diesel energy as I've mentioned. It will leverage powerful winds at high altitudes, at its seashores, and then the diesel generators. We have the existing power system in Cartwright. Cartwright has 4 diesel generators, 2 of the 450 kilowatts, and then 1 of 600, and the other one is 1,050 kilowatts. They operate to supply electricity. At any point in time, 2 diesel generators are running. These graphs show the average annual load of Cartwright from 2022 to 2023, and the average annual load for that year amounted to 4.6 megawatt hours with a net peak of 902.24 kilowatts. In Fig 4, we have the graph showing the timestamp data of the generator output in Cartwright. Fig 5 is showing the daily profile, seasonal profile, and the yearly profile. Please. On this slide, we'll be talking about the wind energy resources in Cartwright. From Fig 7, that is the one on the left, it can be seen that the peak wind speed occurred between December and January, while the lowest wind speed occurred between July and August. The monthly timestamp data in Fig 6 helps us to see the hourly behavior of the wind in Cartwright. And the wind data obtained from that, we can see the monthly average wind speed amounts to 5.97 meters per second. On this slide, we'll be talking about the solar energy resources in Cartwright. The graph shows the average annual solar irradiance of average of 2.87 kilowatt hours per meter squared per day. The month having the most irradiance is May, followed by June and July, as we can tell from the seasons when it is summer. So I'm going to be passing the presentation to my colleague Jonathan right now. Thank you.
Hi everyone. So I'll be taking us through the methodology, straight through the HOMA design and our results. So we executed this project through 4 steps. So first of all, we got the load data via NL Hydro. So we got the data, we cleaned up the data, and then we analyzed that particular data for Cartwright. The second step was to design the system using HOMA Pro software, taking into consideration each equipment that will be needed to meet up to the load data that we received from NL Hydro for Cartwright. So the third step was we assess the system costs of the hybrid system, and then we also take into cognizance the levelized costs of energy. So it will tell us if we are going to get an optimized result at the end of our design and our simulation. Then lastly, we had a detailed design, modeling, and simulation using MATLAB stroke Simulink. So going forward, looking at the entire system configuration and then how we design the system. So all of the components that we need or that we used are all here. So we have used about 5 equipment. So the diesel power generating unit, which is about 500 kilowatts diesel generator, our solar PV system. So this is the model that we used, our wind turbine, the battery storage, and then the converter, which is a 1000 kilowatt converter based on our peak load, which is about 902.24 kilowatts. So this is the system outline in exactly in HOMA when we are done making that design. So we can see from this now that we can see that we have about 12,811.12 kilowatt hour per day and a 902.24 kilowatt hour peak. So this is the electric load of Cartwright based on the equipment, based on the data that we got from NL Hydro. So we use the 500 kilowatt CAT generator, which is part of the generators that we have out there in the Cartwright already existing. And then we used a wind turbine, a 100 kilowatt wind turbine. We used a Trojan battery, which is about 225 Trojan battery. And then for the same thing, we used the solar panel. So the solar panel is about 0.325 watts. Okay, so looking at the entire system design, so we can see the capital cost of each particular equipment that we used in the entire design. So all the costs was sourced out by us, looking at the entire equipment that we used for the design, taking into cognizance also the diesel generator that we have on ground as well. So we can see each of the equipment, the load per day, and as well as the exact capacity of each particular equipment. So taking us through, you can see the total load connected, which is about 12,811.12 kilowatt hour per day. Our daily peak load limits, which I explained before now, which is about 902.24 kilowatts And then our solar PV system 0.32 kilowatts, our wind turbine about 100 kilowatts each. Then our diesel generator, CAT 500 kilowatt generator, and then the frequency of 60 hertz. And then our battery storage, which is about 3.06 kilowatts, 257 amp per hour, and about 30 strings in parallel, and 360 volts voltage. So our inverter obviously is about 1,000 kilowatts. Okay, so going forward, we can see the entire design of the system. So this is the layout of the entire system, how we it's going to be laid out there in Cartwright, exactly when the system is being commissioned. So this is just a design that we made in SolidWorks to give you a holistic view of what is expected of the project. So going forward, you can see that the designing the system, the specification of each equipment. So we will know that yes, it meets the requirements for our load for Cartwright that is currently being fed from the diesel generators that are on site. So here we are having the specifications for the wind turbine future. We are also having the specifications for Eaton Power, that's the inverter. We are the converter, sorry. We're also having the specification for the battery. And then looking forward, you can see the specification details for the generator, as well as the specification details for the solar panel. After the design of a system, we did calculated the results so we can be able to know if the system is going to meet the needs of Cartwright. Okay, so this is part of the results that we got, and looking at each necessary components. So first of all, we designed a system to be able to meet or to use more of renewable energy and very less or minimal of the diesel energy that we already have out there in Cartwright. So our constraint, we used an 80 to 20% constraint, so 80 to renewable energy and then 20% to diesel energy. Okay, so looking at this now for the electrical parts, we can see that the hybrid system, this is after the design and the simulation was done in Homer. So the hybrid system produces about 9,997,676 kilowatt hour per year, right, with a percentage production of about 57.7%, 41.5%, and 0.756% to wind energy, solar energy, and energy from the diesel generators, respectively. So our renewable fraction of about 98.4%, which is actually very good. And we have an excess electricity of about 4.828299 kilowatt hour per year. So looking at this now, you can see that for our excess energy, we can be able to give the plan actually is to be able to feed the neighboring communities, which are also spending excess of their funds in diesel purchase and running their diesel generators. So looking at this particular system, we can be able to generate more money by selling this excess energy to both Blacktickle and Sandwich Bay, which are the surrounding communities of Cartwright. So if you can look down here in the entire system, you can see that the monthly electric production from January straight up to December was simulated and it looks good. So in all, we can see that it's just bare minimum during the top times of winter that we had the generators running based on the demand, which can include heat to be able to keep the people of Cartwright warm during this scorching cold period. And yeah, you can see that we have about 57% of the total energy produced coming from the wind turbines, which obviously during this period we have high wind speeds, as well as 41.5% coming from the solar. Okay, so this is the electrical result that we got from Homer. Now going forward, you can see the full summary. So the reason why we brought this is to see to show us the gains that we get from this hybrid system using a more focus on renewable energy. So if we're focusing more on renewable energy, we could see that the total fuel consumed for the year, if this system is being executed or implemented, definitely we can see it's about 20,116 liters per year, taking it down from a whopping about 1.8 million liters to about 20,618. That's a lot being cut down based on this our system. And you can see that the diesel generators run optimally during the winter and then in August due to the fish plant. Yes, so they have a fish plant and it runs only during the summer period. So that period, they actually demand more electricity, and that's the only time that you see the generator coming up during the summer. Right, and then lastly, saving diesel costs and carbon emissions. Yeah, that cannot be overemphasized because one of the reasons why we do this is to promote green energy, which is renewable energy, and this particular design is going to help us to achieve that and cut down a whole lot of emissions coming out from the generators and stuff like that. So onto the next one, we can see the system cost. And categorically looking at the system cost, you can see that a whole lot of positives coming out from this. So for the CAT generator, the only thing that we're getting there is the operational cost since they are already existing in the plant. So the initial cost from the CAT generator is actually zero. So it's just the operational cost that gives us some figures there. So for the entire system cost, you can see that the total cost of the hybrid unit system is about $30.4 million. So that's a huge investment. But in the long run, over time, you can see that this particular system is going to give recoup this particular cost that's going to be spent in this particular project. So the operating cost of the system is about $1.09 million. That's the operating cost of the system. And then the levelized cost is about $0.3544. So this is talking about how much per kilowatt is this particular hybrid system cost. And it costs about 0.3544 per kilowatt, which I think is actually a good design system. So I'll leave this to my next colleague, which is Raymond, to talk to us about the simulation and modeling in Simulink. Thank you.
Hi, Professor. I will be taking the dynamic modeling section. My name is Ore Raymond, and we're going to be talking about the dynamic modeling section of this project. And it has to do with two softwares. Basically, we have the MATLAB and the Simulink, which is also part of the MATLAB software. And we want to analyze and simulate the system behavior in order to get the feeling of the system. We would have to run it through a Simulink model where we will put the inputs, the varying inputs, the fluctuating load as from the load data to simulate the system's behavior in order to predict its real life output. To achieve the dynamic modeling of the system, we have to look at it component by component. We've subdivided this system into the solar PV, the wind turbine, the diesel generator, the converter, and the battery storage system. In the PV solar system, we have modeled the PV arrays because the PV arrays are going to be arranged in an area. So we are going to calculate how much input do we get for the area, how much kilowatt hours are we going to be getting from the irradiance data. The irradiance data is going to be fed into the PV array. We'll simulate it and we'll also get the output, which is going to be fed into the DC bus. From the DC bus, it is going to be fed to the inverter and also to charge the battery, especially when the power is excess. We got the input raw data and we are feeding it into the wind turbine. It's simulating how the wind turbine will operate under varying speed of wind. So under varying wind speed, we are going to have the monthly wind speed of the turbine, which has been taken from the HOMA software, and also we want to generate power each, because we are going to be having a wind farm which has the power. Each turbine is having a power of 100 kilowatts. From our HOMA design, we have about 30 turbines which will be generating a collective power to meet the need of the customers in that grid. Now we move on to the diesel generator. We also model the dynamic response of the diesel generator. The diesel generator is going to be serving as a baseline supplier of power in the system. In other words, when there is the peak hour loads, and also when is going to provide a steady baseline level for the load supply. And we've taken a 500 kilowatt generator. The main components of the generator have been listed. We'll be looking at the mechanical input, the excitation system, the diesel. It has a governor. The governor is actually what reacts to the dynamic changes in the load. When there are fluctuations in the load, the governors will respond to activate the swing of the generator prime mover to make sure that the synchronous generator is generating the sufficient power to meet that load demand at any given point in time. And after that, we'll move into the next section in our dynamic modeling. And we are in the section where we are talking about the converter and the battery storage system. It features a bi-directional battery charging controller, and this controller also serves to make sure that the battery state of charge is maintained at the time when the battery state of charge is dropping. The bi-directional controller will take the excess power from the PV to charge the batteries. And also, when the inverter needs power, the bi-directional controller will also be responsible to take that power to the DC bus to supply the inverter. So in this system, we have employed a full bridge inverter, which is it has a voltage source controller which controls the output to and also make sure that the system is working in a stable manner. Conclusion of this project, we've been able to demonstrate that we designed the hybrid power system leveraging on the HOMA software, also using the MATLAB and Simulink to model the dynamic responses of the system and to analyze the system under those conditions. However, the project is still in progress, and there's future work to be done with our simulations. Would have more conditions to be put in, and we'll do more economic analysis of the system, which is not permitted because of the time constraint. And also, when we have the hybrid power system, we'll demonstrate that we can have a significant reduction in emission, and we have been able to also save costs, running costs of producing electricity in the community. Thank you very much. Here are some references which were used in this project. Thank you for your audience, and if you have any questions, you can drop it in the comment section below. Thank you.